will be Act to C and the C to Act, POMDP planning for object search in Clutter. The presenter is Li Junhun from National University of Singapore.
Alright, good afternoon, ladies and gentlemen. Once again, my name is Junhun. I'm from National University of Singapore. Today, I'd like to share with you my work on Act to C and C to Act, POMDP planning for object search in Clutter. It's a joint work with my supervisor, David Xu, and Wei-Sang Li. Searching an object in Clutter environments is a common practice that every one of us here perform on a daily basis. When you cook, you search in this jam-packed cupboard to find the right ingredient. When you feel thirsty, you search in this cluttered refrigerator to get a chilling beer. For all the tasks, we unconsciously deploy the strategy of Act to C and C to Act. Here's one example. We want to get this chocolate jelly old pudding box, which happens to be occluded by this biscuit box. So what shall we do? We act to remove the occlusion so as to see and review the object behind for easy grasping. So what is really behind this simple but powerful strategy is the idea of the integrated perception and planning. So based on our perceptual input, we plan a sequence of actions to find objects. But in a clutter environment, the objects occlude each other in a really complex way. So the robots only have an incomplete knowledge about the environment. In other words, uncertainty. So considering finding a Coke can from this fridge full of beers. I know many of you here are beer lovers, but anyway, I want to find a Coke can. So can a robot do that? Well, it is extremely hard for robots to find a Coke can, because due to occlusion, the robot only has a partial view of the objects. So it might be uncertain about the true type of that object, whether it's a beer or a Coke. So, but can we apply the strategy of Act to C and C to Act to help the robots? And it comes down to the question of how to plan a sequence of actions to move objects around and to find the target object we want, while hedging against the perceptual uncertainty due to occlusion. And is there a systematic way to achieve this? And yes, in this work, we map the problem of object search in Clutter as a partially observable Markov decision process, in short, POMDP. And then we adapt. POMDP is a principal framework for planning optimally under uncertainty. And then we adapt the state-of-the-art online POMDP solver, Desktop, to solve our large POMDPs. And through experiments, we show clear performance gain over other 3D approaches. So let me now jump into the problem setup. The objectives here is to, in a clutter environment, plan a sequence of pick and place actions to find the target objects efficiently under severe occlusion. Here's the setup. In simulation, again the BREF simulation, we have a shelf on which the object could be placed. We have a kinetic sensors with a fixed view to capture the environment. And we have a table here to which the target objects will be transported. And we have 6 types of objects which can be distinguished by colors. And across all experiments, the target objects is this purple, blue cuboid. We model the problem as a POMDP. So for the POMDP, the state space contains the poses and the types of every object that present on shelf. And the discretized state space is as large as 10 to the power 32. For the action space, the robot can either move object inside the shelf or outside the shelf if there is not enough space to move object inside. And there are more than 1,000 natural paths of action to take. And here we assume the transition function is deterministic. For the reward function, we assign a small cost to move object inside, a large cost to move object outside, and a large penalty for any invalid actions, meaning any action that will result in collision among objects. And finally, we give the robot a reward for successfully retrieving the target objects. Next, the observation model. On the left are the kinects, RGB, as well as depth image, from which an observation will be extracted. The observation will contain the attributes of each observed cluster. The cluster is the result of our segmentation and object recognition module. So it will contain the estimated position as well as the most likely type of that object. Uncertainty modeling is the key in this problem. And here we model the perceptual uncertainty due to occlusion. So the intuition is that the more an object is occluded, the less confident it is about the true type of that object. So formally, the observation function is defined as the probability of observing Z an observation given the state F prime and action A, which can be further decomposed into the products of the probability of observing the ice cluster's attributes given the ice object state as well as how much this object is occluded by other objects. And we learn this observation function offline and store it as a table which can be referred to during online planning. The solution to POMDP is a policy which maps from the belief B to an action A. So in order to choose the best action to take, we need to search in a belief tree. So start with the current belief, B0. We first need to expand the tree by trying out all possible actions. And due to perceptual uncertainty, we also need to consider all possible observations. After a few steps down the tree, as you can imagine, the size of the belief tree explodes. The curse of dimensionality and the curse of history is what will make POMDP hard to solve. So luckily, the stabilized POMDP solver DeathPot come to a rescue. So the idea of DeathPot is that rather than considering all possible observations, it only uses k-sampled scenarios, which should largely reduce the observation branching factor, which allows for real-world applications. The previous work has successfully applied DeathPot for real-time autonomous driving among manufacturers. But still, in our problem, our action space is huge. There are more than 1,000 number of possible actions to take. So I'll go here to further reduce the action branching factor. How do you do that? We first exclude all invalid actions. And then for the remaining actions, we use heuristic to keep the 10 most promising actions to further expand the tree. And this allows us to further bring down the complexity tremendously, which allows for efficient tree search. And here is the other experimental results. We compare our approach with two other baselines. So one is the grid baseline. We try to move away the most probable blocking object with the least cost. The other baseline is the out-only baseline. We try to move out the most probable blocking objects one by one until the target object is found. And here are the results comparing our approach DeathPot with the grid approach on 5 test cases. The horizontal axis represents the 5 test cases, and the image below represents the initial configuration of the scene. And the vertical axis is average discounted reward over 100 runs. The out-only policy, baseline, which is not shown here, is worse than both greedy and DeathPot approach because the cost of moving object out is large. And as you can see here, our approach DeathPot can achieve higher or equal reward compared to the grid approach. But in some difficult cases, the grid approach may even be stuck and cannot retrieve target objects. Here's one example. Here is the initial view of the scene. As you can see, our target objects is occluded by the orange box. So let's see how the grid algorithm performs. It first moves the orange box to the left for two reasons. So one, it prefers to move object inside the shelf rather than outside because the cost of moving outside is large. Second reason, there's no space elsewhere inside the shelf to move the orange box except the left part of the shelf. So the next step, the grid algorithm now you observe the scene and realize the target object is still being occluded by the orange box. The next step is move the orange box to the right. The same reasoning applies. And then left and right, and you will never get out of the loop. Where our approach is able to find the object efficiently by taking into account the long-term effect of action. So here's how that will do. So the reason about, in order to move the orange box to fully review the target, it will need to create some space to move the orange box. So you will first move this pink cylinder to the right, so create some space in the middle. And then it's able to move the orange box further to the right to fully review the target objects for easy grasping. So this smart behavior is due to the fact that we are taking into account the long-term effect of action rather than its immediate effects. All right, to conclude, in this work, we model the problem of an exertion clutter as a POMDP, and we adapt the depth path to solve market POMDP. As for experiments, we show our approach outperform the grid approaches, and to be able to find objects efficiently and robustly under conceptual uncertainty. Thanks so much.
Any question?
Yes?
So I'm curious, is your action continuous or is it
Discretized. Discretized action. So you can move, for example, you can move object from XY position to another XY position. Discretized.
And how do you choose it so that it's narrowed down to say 10 actions?
Action, right.
Like how do you use this?
How do you use, we first exclude all embedded actions, we forget about all embedded actions, and then we use heuristic to sort the remaining actions and keep the 10 most promising actions. So the heuristic contains two parts. So one is how much reduction, how much occlusion can be reduced after taking these actions. The second factor is the cost of such actions. So we use such heuristic to sort it out the actions and keep the 10 most promising actions for the expenditure.
Thank you. So some more questions? Okay, so let's thank the speaker again.